Alright, in this video I'd like to talk through the conceptual ideas about work and energy that we'll be using in this unit. First, work. What is work? Well, we can define work in a couple different ways. We can say that work is some force acting through some distance. You take a cart of groceries and push it across the grocery store. You're using a force, and you're pushing it through some distance. You've done work on that cart of groceries. You walk up the stairs, you're doing work against gravity, and so on. I'm going to add a little parallel sign here to remind us that work is actually the only forces that contribute to work are forces that are acting in the same direction as distance. So that's work. Work is force acting through distance. But we can also say work is equal to some change in energy. When you do work on something, you're changing its energy. When you lift up some heavy object and place it on a shelf, you're doing work, a force acting through a distance, to store up potential energy. When you throw a baseball, you use a force acting through a distance to give that baseball some kinetic energy. So you could say work is a force acting through distance. You can also say work is a process that changes the energy of a system. Now, introducing the idea of energy, what is energy? Energy, you could argue, is the work in something. If an object is rolling, like a bowling ball rolling down the bowling alley, that bowling ball has a form of energy. Work is stored up in that bowling ball, and when the bowling ball hits the pins, it does work on the pins. It exerts a force through some distance on those pins. Now, normally with energy, we talk about forms of energy. We just mentioned one form of energy, kinetic energy. Since this is a quick summary, I'll just show you the equations briefly. Kinetic energy, K, is 1/2 the mass of the object times the object's velocity squared. Notice the squaring, that's important. If you have an object that has twice the mass, it will have twice the kinetic energy. But if you have an object that is moving with twice the velocity, doubling velocity and then squaring it is going to give you 4 times the kinetic energy. So two Ford Tauruses driving down the road have the same mass. If one of them is going at 50 miles per hour and the other is going at 25 miles per hour, the faster Taurus has 4 times the kinetic energy. And as a result, it would take 4 times the work to stop it. All right, so that's one form of energy. Kinetic energy is the energy of motion. We also will have talked about gravitational potential. I'll say potential with a little grav. Gravitational potential we often write as UG. This is energy that is stored against gravity. So when you lift something up, you're increasing its height. The amount of energy that it has stored up against gravity is the mass times g, 9.8 as long as you're on Earth, times your height. Another form of energy that we'll talk about in this unit is elastic potential energy. So consider a spring. When you stretch a spring, you're storing up energy in it. When you let it go, that energy could be unleashed as some other form of energy, or a rubber band. When you stretch a rubber band, you're storing up elastic energy that can then be released somewhere. How much energy is that? Well, here's the equation for elastic potential energy. 1/2 kx squared. Notice it has the same form as this kinetic energy, and that you'll see a lot in physics. Half a constant times a variable squared. You'll see in calculus that when you take the first derivative of these with respect to that variable, you end up with mv kx. There's a deeper meaning there. But anyway, the k here is the spring constant, which is the stiffness of the spring, and the x here is the stretched distance. So if my spring is here, it's unstretched. So from this location to there, the stretched distance is from there to there. That's what I would put in for x. And as usual, for all of these quantities, Masses we would write in kilograms. Distances and heights we would write in meters. And we would get energy in a new unit called joules. Joules named after James Prescott Joule, a British scientist. So kinetic energy is measured in joules. Gravitational potential energy is measured in joules. Elastic potential energy is measured in joules. And since work is a process that gives energy to a system, work is also measured in joules. Now, from our definition of work here, work is force times distance. Force is newtons, distance is meters, so a joule is the same as a Newton meter. Okay. Now, one of the things that we'll see in this unit is that when work is done on an object, it contributes energy to the system, or sometimes it takes away energy from the system, if it's work done by friction or something like that. But once there's energy in the system, it sometimes can change forms from one thing to another. I'll give just a simple example. If you have a roller coaster that's riding along on the track here, maybe this is our roller coaster up here, just at the precipice, ready to start rolling down the track. If it's not moving much, it doesn't have kinetic energy, so the kinetic energy here would be 0 joules. But this roller coaster is way up high. It has some height here above the ground, and we would call the energy that it has stored up against gravity, we call that gravitational potential energy. And if I needed to find out what that is, I could say mgh, the mass of the roller coaster, times 9.8 times the height in meters. Now, as this roller coaster rolls down the track, gravity is doing work on the roller coaster, and that work is converting gravitational potential energy into a whole lot of energy of motion. So by the time we get down to the bottom of the track here, now its height is 0, so it will have no gravitational potential energy, but it will have an awful lot of kinetic energy. And in this case, we see an energy transformation. The potential energy stored in the roller coaster here is unleashed to become kinetic energy down at the bottom of the track. Now, in truth, there would also be some friction. Roller coasters ride on wheels with bearings, and the bearings would have gotten warm. It also has to push air out of the way. That air resistance would take some energy away. So in real roller coasters, they'll have slightly less kinetic energy at the bottom than the potential energy at the top. But if we consider an ideal roller coaster, then all of the joules here become joules of kinetic energy here. Well, what about at this loop spot? Well, it's not quite on the ground, so it does have some gravitational potential energy. It has a new height here. Maybe it's half the initial height, so it would have half of the gravitational potential energy. But it doesn't use up all of its energy to become gravitational potential, so it's still going to be moving. There will still be some kinetic energy here, which we could quantify with this equation again, 1/2 mv squared. So the idea here is throughout this roller coaster ride, there's going to be a transfer of energy from potential to kinetic, back into potential, and so on. And the assumption we make in many of these cases is what we call COE, conservation of energy. Whatever total change in kinetic energy there was, plus whatever total change in gravitational potential energy, plus any change in elastic potential energy, plus any work that was done to friction, all of this has to equal 0. This is what we call the conservation of energy. Considering the roller coaster going from the top of this hill to the bottom of this hill, our gravitational potential energy drops. Let's say it loses 1 million joules of energy. Well, there's not any elasticity in here, and if we assume friction is negligible, then its loss of 1 million joules of gravitational potential energy will lead to a gain in kinetic energy of 1 million joules. So using these equations to quantify things and keeping in mind the conservation of energy, we can begin to solve problems with this concept of work and energy. I'll try to make a few other videos showing a couple different types of problems you can solve.